So I'm James from KDAB, and this is Pepe. We are one of the people working on Qt3D. Two more of them are helpfully sitting in the front row, so if I get anything wrong, they can correct me. Yeah, we've been working on Qt3D since the end of last year, really, if you actually want to go to the next slide. Sorry, yeah, we're going to introduce Qt3D and the history, which is important, and what we're aiming to do with Qt3D, because obviously 3D is a vast field with many existing technologies, which you may already be familiar with, and be using or have used. So the question is, why are we working on 3D code at all in Qt when there's other solutions? And then we're going to show you some examples using QML, and then talk a little bit about the structure we've picked for Qt3D, something called an entity component model. And then we're going to show you some C++, and then some more complicated stuff, and then we'll finish up. And this is very much an introductory talk, because if you are already an expert in OpenGL or 3D systems, you should go to the following talk by my colleagues down the front, which goes into the details. We're not assuming any prior knowledge of OpenGL or 3D in this talk. So if you know nothing about 3D, it's fine for you to be here, like my wonderful manager over here, who is completely ignorant of all topics regarding 3D, right, Kala? If you already know about OpenGL, then some of this will be familiar to you, but we need to show you how we're expressing some standard 3D concepts in the Qt3D world. So, next slide, please. Oh, you can do it. Okay, so this is Qt3D 2.0 we're introducing. We need to talk about the past and what came before. There was a Qt3D 1.0 developed by the Nokia Brisbane office, which went through various preview and lab statuses in the history of Qt4. And the first major release, 1.0, of course, as first releases usually are, unless you're Google, was targeting Qt 4.8.1, it says here, I can't even remember, but not included. Unfortunately, because that was a somewhat turbulent time in the evolution of Qt and Nokia's relationship, it was also the last release of Qt3D. And there's never been any Qt3D in Qt 5. So it was in such a sort of new and incomplete state when Qt 4 was created that it just didn't make it into Qt 5 at any point, and that's why we've stepped in to create something that hopefully will fulfill the same role and exceed it in many ways. So yes, Qt3D 1.0 had C++ and QML APIs. That's good. That obviously, you'd like to be able to do 3D work easily, and QML is a good way to express that, to define things without writing compiled code. But equally, in a 3D application, you very commonly have lots of data or large amounts of data from a medical scanner or a GIS survey or a CFD solution, and therefore very likely you don't want to handle a gigabyte of data in QML. You're better to do it in C++, and so there was an API, sort of. And what could you do in Qt3D? You could define geometry and materials and how the whole scene looks. If you're not unfamiliar with 3D geometry, we mean cubes and cars and bits of terrain and all the other things you can see on the screen. For materials, we mean how things look, textures and colors, and how things interact with light. Phong is one of the lighting models that's very commonly used in 3D and everywhere. And of course, Qt3D 1.0 could do it. And then there's many other things you need to define for a 3D scene, cameras and lights and so on. So it's a pretty, all the basics are there. And then there's a very simple rendering engine in Qt3D, and that's really where the problems start. I could do some particular kinds of rendering. There's a list of them up here: solid colors, Phong lighting, and basic texturing. But there was really no configuration. The renderer you got in Qt3D 1.0 was what you got. It was simple and it would work everywhere on OpenGL 2 and OpenGL ES2, but it had some ways to configure it a little. I can hardly even remember what they are, but essentially you've got one way it could work. Yeah, and you couldn't extend the scene to do non-graphical things, which usually in a 3D scene there's a non-graphical component to what you're doing as well as the graphical component. So, for example, physics or audio simulation or other kinds of animation potentially. So the simplicity is a problem with Qt3D 1.0, but the biggest problem is performance. Nearly always, if you're doing 3D work, performance is important. You can't just ignore it like you maybe can with 2D or traditional desktop things. Normally, performance becomes a problem quickly. So a 3D rendering engine that's slow isn't a very useful 3D rendering engine, and that's generally a problem you encounter if you try to build a large scene in Qt3D 1.0. Of course, the thing is that nobody ever built a large scene in Qt3D 1.0. I've asked everybody I could find who used 1.0, and nobody built something that was actually even remotely large because it simply wouldn't scale. It was fine for building tech demos, but you couldn't scale up to large scenes. And then, of course, finally, the development stopped when Nokia ditched Qt. So there's some problems. So then we thought we'd try and fix the problems, because at KDAB that's generally what we try and do, is fix people's problems. Often we're fixing customers' problems, but in this case we're fixing a problem for ourselves, although partly because we're sick of customers having this problem over and over again. So rather than writing it that's solving the problem for each customer, we'd rather solve the problem once, put it in Qt, and then we do less work each time for the customer's problems. That's how open source works. So we did a bit of a redesign, initially a bit of a redesign, and then increasingly ended up being really a rewrite. And in particular, we have a data-driven renderer. So you can say how the renderer works, what it does and how it looks, using data without writing more code. And this is a really cool feature. We're going to explore in a bit, although we're going to explore it just the surface. Again, for the details of how you do this, you should go to the following talk. Oh, go back one bit.
Oh, sorry.
Was that intentional or unintentional?
No.
Okay. And then secondly, we're using this thing called an entity component design we're going to talk about, which is found in several modern 3D engines and 3D game environments and 3D systems. And it's becoming not quite a standard, but a very common way to manage 3D scenes to avoid a multiple inheritance type explosion of functionality in the classes you create. So let's come on. Right. So one thing was to ensure that we kept and extended having a QML and a C++ API for everything. We deliberately got two examples which look at the same on the screen, one of which is pure QML and one of which is pure C++. Because we know that you want to do things quickly in QML, but you need the option to go to C++ for performance. That's one of the goals, and we feel we've achieved that. The next one is it should be extensible. Some people in this room don't care about fancy rendering techniques. They just want to take a rendering technique that comes with a library and be able to visualize stuff in 3D. You know, the basic forward technique that 1.0 had would be enough for them. And we've got that basic rendering technique in Qt3D too. But many of you out there want to do something different for, data visualization reasons, or to make it look just cooler for your marketing department, just to do any of the wonderful rendering techniques you can find on the web that do effects and glows and shadows and all those things. So we let you, the user, define how rendering looks. And we also wanted to ensure that we could go beyond just plain 3D geometry. So we could do other types of spatial systems like simulation, physics, and audio in the same 3D environment or spatial environment. And obviously the other problem we had to solve or address was efficiency. So we have a threading design based on Threadweaver, actually, from KDE, which tries to use multiple cores on your CPU and obviously also create rendering batches which are as friendly to your GPU as possible. Without getting into too much into performance here, because this is an introductory talk, in order to get good graphics performance, you need to be using all the parts of your computer as efficiently as possible. That means CPUs, plural, even on a mobile platform potentially, and also the parts of the GPU you can. And this generally involves lots of scheduling and balancing and batching and those kind of jobs. And we've tried to design an API that will let us do that internally. And the goal is to offer potentially an alternative to things like VTK and OpenSceneGraph and other visualization solutions. I mean, obviously, you might already be using some of those things and have good reasons to, but there's areas where we can certainly offer more performance than those and potentially other features as well. But of course, it's just another choice we can put on the table. We have a long list of non-goals, although you may disagree with some of them. We are not trying to invent yet another universal does-everything 3D engine, because there's no need. So we're not trying to, for example, recreate Unity in Qt. We could do it, but it would require an entire team. And Unity does being Unity very, very well. There is no point recreating Unity. So quite apart from manpower, I just don't want to spend my life competing with Unity when they're already doing the job really perfectly well. We're looking to make a small core for 3D that saves recreating those parts over and over again. And then if people want to build on top, they can. But we're not going to make an all-encompassing platform out of this. Similarly, we do not want to force everybody to use the same rendering techniques, which was a major flaw of 1.0. Because essentially the belief in some engines is you to find some predefined techniques which are useful, and everyone else has to just work with those. But we will obviously provide some basics, and they can be customized. And obviously the other thing we're not going to do is duplicate things which are in Qt GUI. So the layering that we're aiming to achieve here, and that we agreed with the community as we developed this, was that things which everybody doing OpenGL work would use go into Qt GUI in the Qt OpenGL classes. So Qt OpenGL texture, Qt OpenGL context, and all these classes you may or may not know about are in there in Qt GUI. And you can use those and not use Qt3D. And we're not going to try and move those classes into a Qt3D module. This is purely optional stuff on top of what's in Qt GUI. If you want to use this 3D environment, you can use it on top. If you want to use a different 3D environment, it'll work side by side. It's just purely, we're layering the stack to not introduce dependencies in that direction, is the intention. Okay, I think we're going to see an example now. Hooray.
Yeah.
We're going to see an example purely in QML, because again, this is what the first example from QtDD14 was. So we're kind of replicating the original demos from that with our new QML syntax. And we're going to see a couple of things. We're going to see a scene, so a collection of objects in a world defined in QML. We're going to see a frame graph defined in QML, but a very simple one. And again, we'll come back to what we mean by the frame graph. I'm going to see some simple animations that we get essentially for free because we're using QML, and QQuick 2 has an animation system we can borrow.
Okay, let's have a look at the code.
Run it first.
Of course.
They're waiting on bated edge of their seats.
Yeah, I've pushed all my code into the Qt3D repository, so I'm just running the examples straight from the repository. This is code.
Yes, everything we're running here is pushed to
and this is
called
simple QML because it's really simple.
In the tradition of all 3D demos, it's geometric primitives moving around. Sorry about that.
Yeah.
But we need to keep it simple. So
you can move the camera around using your mouse or your keyboard. You can go up and down, move closer or far away. And it's just not particularly exciting. But
not very exciting at all, but it works.
Shows that we have something there. Let's have a look at the code. There are basically two things interesting here.
Oh, actually, we should say, although this is pure QML, there is a main file.
Yeah. First one, oh, sorry, let me close that. Can you read that? Yeah, looks good. Okay, yeah, let me guide you through this main function. Well, it's pretty much any main function you can see when using Qt. It's just like those 5 or 6 lines of code. We create a Qt GUI application object, which is the normal stuff. And then we create our window class, which is Qt3D quick window. It's the window that can host QML 3D stuff. We have this small call here, register aspect. We'll come to that in a moment. But basically, what that says is that we want to render 3D stuff inside that view. We could register more stuff, for instance, physics or audio or that kind of any extra stuff. But
we'll come on to that in a second.
Yeah, in a second. And we're just like, okay, that's your source, that's your root of your QML scene. That's mail.qml, show it, and exec, yeah.
And of course, this is intentionally similar to the same process for Quick.
Right.
It's okay. So the C++ is trivial?
Yeah, the magic is of course here. So there is a bit of going on here. Let's start from the top, where you can see we're importing Qt3D stuff. So we're importing Qt3D types and Qt3D render types. And root is basically an entity component over there. That defines the root of our scene. Everything that we're going to define is a child of that entity node over there. The first thing we define is, of course, a camera. So we define a camera object in the scene. For providing any camera in Word, we need to provide two things. The configuration for the lens, so basically saying what's the field of view, that kind of information, and a position. And we, just like it's QML, so we do that declaratively, right? We say the camera has this nice lens property, and we just say, okay, that's the object attached to it, that's camera lens. And also, camera has a transformation, so we just like assign something to its transform property.
I should interrupt here. We're still reducing how many things you need to write. So for example, there should clearly be a default camera lens here, so you don't even need to write those default values. Yeah. But again, as usual thing, when you provide a default value, it's right for most people, it's wrong for some people. So here we're configuring the camera lens to a particular field of view and a particular set of settings, but we can provide sensible defaults there. So this example will gradually get even smaller.
Yeah, I do apologize if the types are not found. That's actually a Qt creator bug. So if there is anyone who's developing creator
I'm sorry, a Qt creator bug?
Yeah.
Creator has bugs?
Yes, it does. If there's anyone from creator in the audience, please ping me later because I want to solve it. Okay, the next thing over there is that configuration element, which is just trivial, just tells Qt3D which camera we are controlling with the keyboard. So it's the camera we just defined.
And the entire frame graph bit you should ignore, because again, there should be a default one.
Yeah. But basically,
looking at these guys. So that entire section that says frame graph, we're going to come back to, but essentially those are all default values. This is, again, we're still reducing how much you need to write in each example. So we've been copying and pasting this, but we can set these as the default. If you know what some of these things might do, because you know about OpenGL, like what a clear buffer call might do, or what a clear color is, you can probably see really quickly what this stuff is doing. If you've got no idea what a clear buffer call is, or what a color depth buffer is, don't worry, because we'll provide a default value. When you do know what it is, you can change it.
Yep. And then the interesting bits.
This is what will stay. Essentially, nearly everything above will probably go away to not very much.
Yeah, this stuff is that's going to stay. The first thing we create is a material entity, and that small entity over there, just like it's built-in material, it defines the way the shapes are drawn. So it's just the built-in one. We are not specifying anything in that, and so of course everything will be lighted with that like dark brown color. It's just a built-in one, so you just like to declare it and we'll use it. Then we come to the actual 3D stuff in the scene. So we have three things here. The first one is that thing called tur mesh, and that, as you can imagine, defines a torus. So it has a bunch of properties, the radius, the inner radius, the number of rings and slices, because it's still a 3D shape, so we're just like generating its geometry on the fly, depending on those configurations over there.
Again, in the unwritten laws of 3D demos, you have to use geometric primitives like toruses for your first demo, so we are. The next one doesn't, I promise.
Yep. As you can see, that's just the 3D structure of the thing. It doesn't just do anything on its own. We also define another thing, which is a transformation for the torus. So basically, you're scaling and rotating it a little bit so you see it tilted and seen. And then we create an entity, object, which just aggregates everything we just defined. So it aggregates the mesh, the transformation, and the material onto it. And that's our complete 3D shape with a certain transformation and rendered such that it looks like that brownish color. That's the first example of our entity component model. Basically, we're aggregating stuff we defined before. For the sphere, it's exactly the same thing. We first define a mesh, so that's just like a sphere. A transformation, and this transformation is a bit peculiar because we just like using Qt3D number animation in order to rotate it around the torus.
So here we've got a translation followed by a rotation combined, and if you know anything about 3D, if you don't, sorry, again, don't worry, but order of 3D transformations is usually very important. If you get them wrong, then things look backwards. So here, the transform component specifies a series of actual transformations that are made. There's a fixed translation by 20 units, and then we have a rotation, but rather than being by fixed value, we're going to use the Qt3D number animation system. And things are up at the top, we import Qt3D, don't we?
Yes, we do. Yeah. Over
If you
here,
look at
we
the
import
import statements,
Qt3D as Qt3D.
we import Qt3D and the Qt3D rendering stuff, and then we go and import Qt3D and QML. But obviously, we use the renaming feature that you may or may not be aware of in QML to rename a module as you import it. So we just call that Qt3D. And then we can use it down here.
So that's exactly the Qt3D number animation you're already probably using if you're using Qt3D. And it animates the angular property of that rotate element over there. And therefore, this sphere just rotates endlessly. Loops. The number loops is infinite. It's running from 0 to 360. It takes 10 seconds to complete. And again, the last block is the interesting one. We're aggregating the sphere mesh, the material, and the transformation of the sphere into an entity. And that's what gets drawn on the screen.
This is seeming a bit verbose, and why are we separating out these components from these entities? We're going to see why, but the major one essentially is efficient reuse. If you've got, rather than your entity coming from just QML, if you have a model that creates entities, one entity per row, let's say, if it's some kind of model, then you might have hundreds or thousands or potentially tens of thousands of entities, but if they're all using the same mesh, we'll obviously only load the mesh into memory once, and the same for a material or a transformation potentially. So we see over and over again in the clients we work with that one of the reasons their scenes can be slow is that they've got duplication, but they can't express the structure of the scene in a way that the OpenGL can understand. And OpenGL performance is all about being able to reuse and share stuff and then draw groups of things, batches, quickly. This scheme will let us say, okay, all these entities share the same sphere mesh and the same material. Let's draw them all at the same time, and that will make that considerably more efficient. And I don't mean twice as fast, I mean 50 times or 100 times faster. So it's really important that we're able to analyze your scene structure and make these changes. If we couldn't analyze the scene structure that way, we'd be stuck just doing things slowly.
So let's go back to the slide. Let's explain a bit more about what are those components.
Talk in some detail about this thing. So yeah, we have this thing called an entity component system. I wasn't calling it that, but then we kind of did some looking around, and the Wikipedia article calls entity component system, so effectively following what everyone else is calling the system. This is a term you can Google outside us. We didn't make up this name. Scenes, all kinds of scenes, whether they be Qt3D scenes or 3D scenes in any 3D engine ever, usually are a tree, or occasionally, if you're going to get pedantic, a digraph or a directed acyclic graph of nodes. And indeed, that's true for our scenes. So we have a node class, which is what our scenes are composed of. And that's just really a thin subclass of QObject. It adds, I think, one other feature. And then the entire scene is a tree of nodes, in our case. The nodes we mostly care about are things called entities, which is, again, just a node is a subclass of QObject, and entity is a subclass of node. And each entity can have 0 or more components. And we've already seen 3 examples. We've seen a material, we've seen a mesh, and we've seen a transformation. And the point is that you can define more kinds of components. And we can define more kinds of components, but so can you. That's what we're going to talk about, aspects. So each aspect defines a collection of components it can deliver. So we mentioned the rendering aspect. Again, it's applying things like the meshes and the materials. If you imagine a 3D audio aspect based on OpenAL or direct sound 3D features, that would define components like an audio source or an audio listener. If it was a physics aspect, which we're experimenting with, it would define things like the mass component or something about how a spring would be defined. And these are essentially components are like behaviors. They're not a tangible thing. That's what entities are. You create a tangible thing by defining an entity and attaching components to it. And the presumption is if your entity is a icon or glyph or thing you're going to reuse frequently in your 3D scene, of course, QML gives us a component system. We're going to define a QML file, and we'll see this in the second example, for that particular kind of entity, and we'll say what mesh it should have, what materials it might have, and then we'll use that repeatedly in our 3D scene. And again, because we allow full C++ and QML API, you could define your library of entities in QML, but instantiate them and create thousands of them in a loop from C++, and it will all work. So it's a very extensible system, and that extensibility, but avoiding multiple inheritance or other complicated aggregation systems, is exactly why it's become popular in various visualization and simulation environments. Oh, here's the lovely diagram. Yeah. Is this actually UML? You've actually bothered to do proper UML? Wow, haven't done that in a while. Oh, OmniGraffle, okay. I must work out how to read a proper QML, yes. QNode inherits QObject, QEntity and QComponent inherit QNode. If you think these class names are very generic, don't worry, they're all in a namespace, because grabbing the words node, entity, and component globally might have been a little bit cheeky of us. So they're inside the Qt3D namespace. Yes, sorry, if you go back one slide.
Yeah, sorry.
So a entity aggregates 0 or more components. Every component is owned by an entity. Now you can go on. This is the problem we're solving. We have a class, whether it be mesh or a 3D node object. We want to extend it with some extra logic. So we don't want to have to start adding sound limiter functionality onto our mesh class, or adding physics rigid body functionality onto our mesh. That would rapidly get complicated. And you can see what would traditionally happen here. You have some kind of base class, and then you have to refactor everything inherit from the right bases. You get massive multiple inheritance hierarchies. And every time you want to change what components, whether a particular thing produces sound, whether it has physics interaction, whether it's clickable because it does picking, whether it has particular materials or doesn't, you need to change your class hierarchy, which is usually very labor intensive. So that's the problem.
Sorry, that's the problem.
And the solution, as we've already really said, is to use this component-based solution. We simply add an audio emitter to our component defined by our audio aspect into our entity, and we are essentially done. And we're obviously providing the rendering components in this model, mesh and material and transform. Transform is interesting because it's shared by several. Transform set specifies the position of things in 3D space. So obviously the renderer cares about it, but so would physics, so would picking, so would other kinds of data analysis of the scene. So there can be generic components, and there can also be one specific to an aspect. And we're assuming and allowing, because we're trying to keep Qt3D small, that you will be defining your own kinds of component for your application to mix into this. So that brings us to aspects. What's an aspect? It's essentially a plugin, and every frame, it can get to do some work using the threading model that we have underneath the hood. Aspects walk through the scene and find information about entities, such as what components they have. So you can probably guess that our renderer aspect looks for things like meshes and materials and effects and textures. And the audio aspect that we have looks for audio emitters, listeners, but also looks for transformations. A physics aspect would look for masses and collision surfaces. Of course, a collision surface might be a mesh, and similarly, a picking aspect would probably, again, potentially look for a mesh, but sometimes when you're doing picking, you use a simpler mesh for picking and collisions and physics than you do for rendering. So you could have potentially several kinds of mesh attached, and that's still possible in the system. It's good in that we're not excluding any combinations like that. And we have, say, this system based on Threadweaver that triggers work often every frame for an aspect, but potentially just when things change to update stuff. And yes, my colleagues down here will be talking in detail about the implementation of this in the following talk. So yeah, filling this out, we have some of these already. We have an audio aspect and a skeleton physics aspect just to prove the concept. We're not probably going to support those. I'm not sure if we will, but we'll see. We'll certainly obviously support the render aspect, but the goal is really to have some examples, and then it should be easy to plug in your additional ones. Okay, let's see a more advanced example using this. This is now, that previous example was a single QML file. Now we've done this the right way and split it up into several QML files, each of which is simpler. And we're going to get away from boring geometric primitives. We're going to use asimp, the worst named library in the world, to load some meshes onto the screen.
Sorry,
and we're going to use some additional trickery. We're going to do a thing that requires a thing called an off-screen surface. If you know what that is, this shows something that we could do that wasn't possible in Qt3D1. If you don't know what an off-screen surface is, don't worry. Hooray.
Let me move the camera a little bit.
So, we have some meshes. These are both mesh objects we're loading. They both have animations. The planes animation is actually pretty complicated. We're going to see, because it's a sequential series. It does a barrel roll, or probably technically something, yeah, not quite a barrel roll, around the loop. And the whole scene now has shadows working. So we're doing a technique called shadow mapping. Again, you may have heard of shadow mapping. You may not have. Don't worry about it. We're going to show you the code that does it. But if you're not familiar with shadow mapping, it will make no sense to you. Don't worry about that. The point is that it would have been impossible to do shadow mapping using the existing Qt3D architecture because it didn't allow this kind of rendering. And here we can not only do it, we can configure it with no additional C++ code, which is pretty nice.
I also noted that everything is not in that horrible brown color. Yeah.
Oh yeah, and now we have some actual real materials, at least on the torus knot there. Not a torus knot, what's it called?
It's
a trefoil knot. Yeah, we have a different material. And here you can see, by the way, there's horrible pixelation here. This is an artifact of shadow mapping. So we've chosen to do this technique called shadow mapping. You get this blocky effect when you zoom in. That's just what shadow mapping does. If you don't like shadow mapping, you can do a different technique. We're not going to try and say you must do shadows this way, because if you're always zoomed out, zoom out.
Yeah, I'm doing it.
Then it's a great technique. If you know you're going to be zooming in a long way, it's not a great technique. We can't possibly predict for your application if shadow mapping is a good solution or a terrible solution. We're not going to try and decide if it's a good solution or a bad solution. We're going to give you the options to pick and choose and to create your own. And of course, we're going to give some libraries of standard techniques that we know people will use.
Let's have a look at the code.
There's more files, but they're all simple, promise. I think the C++ is identical.
As you can imagine, this is pretty much identical. I'm just doing a little bit extra work.
I'm not sure why we have that connex property. You can tell me later why we have that.
Yeah, it's just like, well, it's simple. I'm just exposing our window in QML. That's, if you know QML, you know what that does. But now we have a whole bunch of QML files. So let's start, of course, from the main.
Okay, I see we had the window. Right.
Yeah.
We've got the window in, so the aspect ratio can be corrected for the window's real aspect ratio, i.e. width and height. Again, I feel like this could be automatic in the default lens. I think we could have a magic value for aspect ratio that says follow what the window's got so things stay in proportion. And then that entire lens section would drop away. We wouldn't need that property. Again, we're going to be progressively making this stuff more automated, and feedback on reducing typing and duplication is welcome. So that's pretty much drops out. Okay, so we still have a camera. We still have this configuration control camera. That hasn't changed. We have a light now. Light is not a built-in class in Qt3D because obviously some scenes in 3D have lights. But if you're doing data visualization, a light I don't know, a sprite-based system, maybe you don't even have lights. So again, we're not even going to predefine a light class. This is a component we're defining here. And we're going to come back to it in a second. So this is just a QML component defined by light.qml over on the left. And then we have some components on our scene. And the rule is basically we configure how the drawing happens, this frame graph, by the components on the root, the scene. We're going to come back to this shadow map frame graph. But essentially, it implements the shadow map technique we just saw. And we'll see a little bit about how it works in a second. It has some parameters, but we'll come back to those. And then we have this ADS effect, which again is defined in a file we're going to come back to, which says, again, some parameters. I mean, again, these are all classes we're defining. This isn't Qt3D. This is us using Qt3D to define these effects and these things. We have our trefoil, which again, we've actually made, and this is what we expect to be doing. We're not just assembling the mesh path here. We've made a new entity called trefoil that defines the behaviors we want, and we'll have a look at it in a second. And then it has a material, and we're actually going to adjust the material here. So if we made a second trefoil, which we could potentially do, and this is obviously something you would do commonly. Pepe, you just want to copy and paste and show this?
Yeah, the problem is that I need to modify also transformation and all this stuff, but...
Yeah, well, don't worry about it. So we could easily add a second trefoil entity. It has all the components defined in trefoil.qml, but now obviously we can still go and get its properties. This is still QML, and maybe we make this trefoil, I don't know, a red color rather than a blue color, because that one currently there is a shade of gray, I think.
Yeah, I can probably do it, like, diffuse color, Qt, RGBA, whatever, right?
This won't actually work because we need to also move these to not be in the same place. Otherwise, they're on top of each other. But the point is, having defined the trefoil entity centrally, we can go and customize it when we use it, as you would expect in instancing entities in a tree. Okay.
Rinse and repeat for the toy plane.
And the same for the toy plane, again. And then finally, we have this ground plane. We're just doing that so you can see the shadow on the ground, because without a ground plane, you can't see any shadows. So those are all defined in separate files. Let's start with ground plane, because it's the simplest one, I think.
Yeah.
So this is pretty common. Again, we have our import statements. So we're defining an entity. This is saying, when I ask for a ground plane entity, what do I get? And we get some components. And defining the components inside, as we're doing here, is pretty common. Although, if for example, we had several entities that might be sharing a mesh, that's why we have this separation of listing them at the bottom, so you could reuse particular components between different entities to save memory. So this entity apparently has a plane mesh, which just does the flat ground. It has a transformation to move it down a little bit in the y-axis, and it has a material, which is just set from a property up there. And again, this is all normal QML, so we can still do things. Components are just objects in QML, so all the things we can do, like using them as types for properties, just works. Overriding the default value of that material from the QML file that uses this just works. Pretty straightforward. Let's have a look at toy plane, maybe? Oh, no, let's look at trefoil first, because toy plane is complicated. So the trefoil knot's very similar. No, here's an example of loading a mesh. So now we're not using one of the boring geometric primitives. We're using a OBJ file to load that mesh at the top of the screen. We still have a transformation. And again, now we have some animations happening. Again, we're using the QQuick2 animation because I'm lazy and I don't want to rewrite new animation code when we have a perfectly good system in QQuick2. So we use the QQuick2 animation system to animate the, what are we probably animating it? Oh, the angle property, sorry, of the rotation. Assemble the components at the bottom, and we're done. You could ask, by the way, if we could automatically guess the components, and we have talked about that, but it has other problems. Because you can have child entities, then there's some minor complications there. So we're probably going to stick with having to write the components the entity uses explicitly. So this one was a little bit more complex, and now we'll go and see the toy plane, which I said has some slightly fancy animation. So the mesh is the same, but now if we look at this transform, there's quite a few different... So obviously it's got the transforms for pitch and roll to move it around. But if you look down here, the translation becomes some more complicated. There's some math terms in there, just doing some work. And then this is using just the features of QQuick2 animations to make the plane fly in the loop and then periodically do a roll and so forth. It's just lots of QQuick2 animations.
And then components at the end.
And in the end, the components are the same.
Okay, let's have a look at something more interesting. For instance, light.
So here's our light entity that we defined. And actually, this is a little strange. This light entity defines a camera. That's because we're going to do shadow mapping. Again, if you know about shadow mapping, this will make sense. If you don't, it won't. This is just showing what we decided to call a light in this particular example was up to us. There's no predefined notion of what a light should be or what it should do. And that's important because in different 3D techniques, what a light actually means can vary enormously, from a simple set of coefficients to something you analyze and look for spherical harmonics to many, many other possibilities. So we shouldn't be prescriptive. In this example, a light is actually a camera because the way we do shadow mapping is render the scene twice, once from the perspective of this light, and then once from the perspective of the actual viewer. So there's a camera inside this light for reasons that will become, well, won't become apparent, but are the case. And like other things, the light has a transformation down here.
Well, there's just like...
Oh, the camera has a transformation,
just
sorry.
camera, yeah.
And that's it for the light.
Yeah. It has a couple of properties over there. You could change, for instance, in your main to move the light around. And
going quickly through these, we have some materials we're customizing. Just want to show this one.
Yep.
Yeah, so this is interesting. So the concept of materials is pretty universal in 3D rendering. But what's changed, in the traditional OpenGL, the materials were actually pretty much exactly these four we have here. These things called ambient, diffuse, specular, and shininess. Anyone who's done 3D in OpenGL will probably be familiar with those kind of words kicking around. Again, if you aren't, they're just ways to customize the color and the appearance of a surface. But here, the parameters this material has are up to us. And we're exposing them as nice QML properties. If, for your particular application, this kind of material system didn't make sense, you could just have a completely different way of parameterizing your materials, but that's okay. So the association of those QML properties in the middle of the screen to these names down here is deliberately configurable, because we want to make sure that you can do any rendering system you like, and many would not use this kind of material system. They would have some other names, other coefficients. There might be only one floating point value, there might be 20. Just standardizing on the standard 4 restricts some people and is unnecessary work for other people. So rather than doing that, we're making this configurable.
Okay.
And this one obviously has some sensible default values to give you the, I think, probably the boring pink color or boring blue color we had. Yeah, that's a slightly blue color, isn't it? Okay, that was the material. Then we're going to come on to some stuff that I'm going to start skipping over the detail now, because you should go to the following talk. There is a notion of effects. An effect is a collection of ways to draw something. And the reason we need a collection of ways to draw things is because not all our rendering systems are the same. Some of them are iPads, some of them are desktop computers, some of them are every other device imaginable. So we need to have a way to have different approaches, or what we call techniques. Again, this is a standard terminology, how to draw things, and we collect those in a thing called an effect. And if we scroll down, we'll see some examples. So the effect defines the parameters it supports. They would correspond to
those properties over here.
Properties over there.
So we're just like, they just get renamed basically.
And then we have a collection of techniques. So for example, this first technique here is relevant to OpenGL on the desktop and the core profile. If you don't know what those words mean, don't worry. Just imagine that you could have a different technique for example, embedded or slow machines versus fast machines. And then inside, we could go and configure the rendering passes, which essentially are ways we draw what's in your scene. So we already saw QML that defined the structure of your scene. You know, you had toy planes and spheres and things dotted around in position. This is now more QML, but it doesn't define the structure of the scene. It's defining the structure of how the scene should be drawn. This is this frame graph description we're talking about. And this stuff gets complicated. Sean and Paul will talk about it in way more detail in the following talk. But essentially, we can configure rendering passes, ways of drawing stuff, using QML. And you could use arbitrary shaders in here and configure other things as well, like the rendering states. Again, these may be meaningless words to you. We provide default values for these things, like we say we provide a default renderer, and we'll actually provide several, is the intention. For example, we'll obviously try and provide a default that's optimized for embedded platforms, and a default that's optimized for desktop platforms, and maybe a few more settings within that. But we're not going to support a library of 50 built-in rendering techniques, because they would instantly be obsolete. 6 months down the line, new drivers come out, new features come out. It's just not a sensible thing to do. We'll define a small standard and let you define your own in addition. And obviously, you don't do this over and over again. Typically, you define your rendering, your effects and your rendering techniques once and use them for the entire lifetime of a project. So scrolling down a bit further, as it happens, this shadow mapping technique is multi-pass, so there's 2 of these render pass blocks. Each one defines a way to draw the scene, and for shadow mapping, you actually draw the scene twice. You draw the scene once from the light, and then you will draw it again to do the scene from the perspective of the viewer. Just how shadow mapping works.
Magic.
If you had a even more advanced technique, sometimes modern rendering systems do 4 or 6 or 20 passes. System will still work. You can still do as many passes as you need. And again, obviously, we try and do sensible default values to reduce repetition. And we're plugging in regular OpenGL shaders here. So one of the things we've tried to ensure is we're not going to enforce any rules on the OpenGL shader language you can write. I need to go up a little bit here. So because of these parameter mappers here, which actually define the names you're using in your OpenGL shader programs, you can use, or indeed may already have existing OpenGL shaders. You can plug them into this system and use them to render using Qt3D, which again is a big improvement over Qt3D 1.0. And I think that's, okay, let's quickly show the frame graph QML just to give an idea of the complexity there. Perfect.
Yep.
But again, I'm going to skip over this, we show the C++. So the frame graph is a bit complicated. I think that's almost enough to say. We have to configure some additional pieces like a render target, and it's a bit more complicated. Of course, there's default values if you didn't want to use this stuff, but we can configure the entire set of this stuff from QML. I think that's enough to say. And of course, these are all the examples that are already included, so you're not going to create this from scratch. You're going to take existing examples of frame graphs and plug them into your application if you need to.
Yeah,
back to the slides.
Let's quickly go back to the slides.
Right, we've said all of that. Yes, this is really repeating what I've said. The way the render works is entirely configurable from QML, that you could do forward rendering, wireframe rendering, deferred rendering. Again, you may not know what that is. Don't worry, it's just another way of doing rendering, which was impossible with Qt3D 1.0. And whatever your requirements, your application, your marketing team, your CTO or CEO who sees something shiny want to do, you have the possibility. But of course, we give you some defaults out of the box. And now we're getting near the end.
Yeah, well, just a couple of slides about.
Now I need to show you the important thing, which is that we can do this in C++. Oh, sorry, have I gone too fast? Yeah, I've said all of this. We can define materials, effects, techniques in QML and C++ to get the effect you want. And yeah, there's some selection stuff to decide what technique is used and which passes are used. Again, if you care about the details of that, go to the following talk.
There's a basic C++ example, which we show you.
First of all, we're on the example. We're going to show you the C++ now because actually, while QML is lovely, again, as I said at the beginning, a 3D application usually cares about performance, and usually if you need to get lots of data, you would do it from C++ rather than QML, potentially. Okay, this is not us running the first example again. It just looks exactly the same. This is written in C++ entirely, but we get the same result. And the complex example we showed, which is a lot of QML, we could do with a lot of C++, but again, it would be boring. And so here is the C++ file that does the example, and I guess it's about 3 or 4 screenfuls long, is it, Pepe?
Yeah, it's very long and it's a lot of boilerplate code, as you could say.
Very long. Okay, if you think this is quite verbose, every C++ API 3D toolkit I've ever used has a fairly equivalently verbose API. I can see one person I know who's using a toolkit nodding at the back. 3D APIs in C++ are inevitably quite verbose. That's why QML is good, because you're basically setting lots of configuration, and QML is great for configuring stuff. That's why we try to make a balance where you can do as much configuration as possible in QML, and then do bits of it in C++. Here we've done the two extremes, everything in QML or everything in C++ to show that it's possible. So we're not going to talk about the details of this. I mean, particularly, this isn't even Qt3D. Configuring a Qt property animation in C++ is boring and takes 6 or 8 or 10 calls. And the same for all our other things. If you scroll up again, Pepe.
Transformation.
Exactly as you would imagine. You create each component using a new call. You set up the properties using setter call, set parent, set camera, set effect, and so forth. And then you add them together. If you scroll down to an example of, add component, where's one? Yeah.
Here we go. Oh, sorry. There we go.
Yeah, adding components at the end. It's just the same stuff, but it's much more verbose because it's C++. But again, I could, now we're creating this torus here, now I could just go and do a for loop, or read an XML file, or query a SQL thing, and go and create 10,000 torus entities in a loop in C++, and it will work. So we've got that flexibility to do which parts we want in QML and C++. Okay. To conclude, I think. Oh yes, what's left? This is still on a work in progress branch in Git, but it will hopefully be on a dev branch very soon. We have lots of work to do polishing this stuff, making it less, removing things which are defaults. We need to do, thank you very much. We need to do picking and give you more examples of built-in aspects. We're not sure which other built-in ones we'll support. We've written demo ones for OpenAL and for physics. We may support those, but probably not, because they're really just proofs of concept. And we need to do better integration with Qt 2 so you can trivially mix Qt 2 scenes over your Qt3D scene and have a Qt3D scene in a Qt 2 item. And we should probably write some documentation at some point, but you guys are smart and we'll figure it out. But we will write some documentation, if only because we're sort of required to. So, to conclude, before we take some questions, it's a QtDD14 is a modern engine for doing visualizing 3D scenes. You could use it to write the next, 3D shoot 'em up game, but probably don't bother, just go and use Unity. But for a lot of less intensive than that levels of 3D visualization, it could be a good choice because it should be simple and lightweight and available directly with Qt. And it's now very customizable using techniques and the frame graph system. If you particularly want to do cartoon rendering or some other amazing technique, you can do so. And yes, the code is on on Gitorius already. And there's a tech preview coming with 5.4. Of course, this is open source, so contributions, feedback are most welcome, and indeed so is criticism. If you don't like what we're doing, you can come and tell us that as well, and we'll listen and smile and nod. Pepe, any other closing remarks?
Always do presentations together with a Scotsman, because they do all the talking.
Thank you very much, everybody. I think we have 10 minutes for questions.
Yes, we have roughly 10 minutes left for questions. It's your turn now.
But first of all, I should point out that the victims for the next talk, stand up, Sean and Paul.
There's a mistake in the schedule for some reason.
Yeah, these are the guys who got left out of the schedule, but they're giving the following talk on the guts of this stuff, which is more OpenGL intensive and more 3D intensive. They will melt your brains if they need to. So, any questions, please?
So I have a short question regarding the user interactions. So in the 1.0 version, you had built-in user interactions in the QGL view.
Right.
And that was always affecting basically the camera, which was implicitly the root node. Mm-hmm. Is that still true?
We don't have a user interaction system at the moment. We have the code for a basic picking system. And because picking is one of those things that varies per target application, we're probably going to make it a series of building blocks. So we'll provide a array intersection picking thing, but you might want potentially, pixel buffer-based picking, or you might want bounding box-based picking, or you might want actual mesh-based, I go and test triangles and ray intersect picking. So we are definitely doing the picking kind of helpers. Whether or not we'll wrap that up into an actual user interaction layer, it depends, because obviously Qt Quick, which we try and follow sort of what Qt Quick does where it's sensible, and it has mouse area and so forth. Whether or not we would do kind of those level of kind of have I been hovered over or not interactions, we need to decide. I don't have a good answer there. Do you guys want to add anything on that? Or? Yeah, we've got some ideas, great. This is an area where we want to hear feedback about what these cases are, because the ones we've encountered is triangle-based geometric picking, which is typically what the CAD guys and the CFD guys want. If your data set isn't like those kind of meshes, you might not want triangle picking, you might just want picking the closest object by distance, for example, and that will be a different system entirely. So again, we don't want to be prescriptive, we want to make sure there's the option to do it the way that works for your application.
Am I right that extending visualization can be made via the techniques, for example, I don't know, to split differently vertex buffer objects or some arrays and low-level OpenGL stuff? Is it possible to make it on the C++ code and to expose some high-level properties to QML? So how to split the additional techniques, the custom techniques?
Do you mean about getting data in, like getting custom vertex data in from C++?
Yes, something
right,
like that.
So that we haven't shown, but there's an API, so you could, we have a mesh API done by pausing down here. So you can define mesh data sources from C++ if you're generating the mesh or the vertex data, the vertex buffers from C++ code, and then you can get those as objects and then use them with the frame graph defined as we've just shown in QML and with other entities defined from QML. You can mix and match together.
Yeah, thanks.
I mean, for sure there's cases we haven't thought of, but please try it and tell us what we've missed so we can we want to make that possible so it's easy to get the data in from the easiest source, whether that's a file or QML or C++, and then combine it without having to repeat everything. This is partly why it's still a tech preview. Like, we'd like to freeze the API, but we know if we freeze the API, we have a different problem. So the more feedback we can get sooner, when we can change the API and fix the API, the better. Usual problem with creating libraries.
Thank you. I totally see the point behind the Qt3D, because it basically, if I understood correctly, fills the gap between I have to do everything myself in OpenGL and I have to bring an external 3D engine in. So, and I was personally very sad when the first version with the work from Sarah Smith was basically dropped. My question is, am I correct that this is going to work on OpenGL desktop, or is it going to be a backend for OpenGL ES as well?
It's already been compiled on ES. It needs a bit more kind of shaking out some problems, but the intention is to fully support embedded and desktop, because I mean, we're mostly creating this because we're lazy. We've done this work over and over again for 5 or 8 or 10 different clients at KDAB who wanted to get a bit of 3D into their HMI. They wanted a spinning car on the dashboard, or they want a spinning coffee cup on the printer, or whatever it is. And we don't want to use a full 3D engine, but writing a mesh loader and a texture class and scheduling stuff and doing all these things again and again is boring. We're going to make that job easier. And so absolutely, I mean, more than half of our clients in KDAB are embedded people. This has to work in embedded. That's a vital core aspect. So yes, it all will work on embedded. I mean, yeah.
That's great. Thank you.
Okay, one final question.
Oh, Mike. Some people fill the audience with their friends. I filled it with my friends who are going to give me difficult questions. Remember how much you like me.
shouldn't do this before I do my talk, but anyway.
Oh, yes.
Just a quick question about the loading of the scene graph in your application. It's all at startup time. Do you have support to lazily load and unload part of the scene graph, or maybe load things as they become visible?
I'm glad he's nodding, because I didn't know the answer to that, and apparently we do.
You can just load it into QML, for instance, to... Yes, sorry. You can just load it into QML, for instance, for dynamically load pieces of, entities, geometry, whatever. And I think there is an equivalent API in C++.
Well, in C++, because it's imperative, you just do the work at the right time. Yeah. The question is in QML, can you delay work?
Yeah, you can.
It's declarative.
Just like you do in QML.
Again, if you were being hyper cautious about when things happen, I would probably use the C++ API to trigger loading the QML at the right time, but that's just because I'm a little bit paranoid. But obviously there are loader elements as well.
Okay, thanks a lot everybody for being here. A big thanks for James and Giuseppe for their talk.